Hello, my name is Jiang Yihua and my advisor is English Lao Shi. Today I'm gonna present the mechanism of CRISPR-Cas12a protein and engineered variant on lambda DNA. First of all, let's introduce what is CRISPR. The full name of CRISPR is the cross-linked regulatory interface short pendilomic repeats, which is an immune response of bacteria against phage. The way it works is when a virus attacks the bacteria. The test protein detect the virus and cut a part of the sequence and bring it back to its home genes. While the next time the same virus attacks the bacteria transcribe a complementary strand of DNA to match the viral DNA in order to resist the virus infection. The CRISPR family can be divided into two classes without its ribonucleoprotein, the RNP, and in the two classes can be further subdivided into three types. Among them, the most widely used Cas protein is the Cas9, this one, belonging to the type 2 in class 2. Moreover, the Cas9 protein is more prone to mutation and toxicity risk. At present, it is more primed to study the Cas12 protein, belongs to the type 5 in class 2. Okay, next, let's introduce about the Cas12 protein, also called the CFP1. The PAM sequence is a recognition sequence for Cas12 protein to target DNA. And Cas12 protein adopts a bell-looped architecture with a recognition loop, the REC, and the nucleus loop, the NUC. And introduce a 6 to 7 anti-staggered cleavage away from the PAM sequence, 6 to 7, in the RUVC and NUC domain over here. And they use optical tweezer to pull in the lambda DNA. And how the optical tweezer works. A laser beam passes through a convex lens, and the angle difference between the input laser and output laser caused by reflection make a force which is called a radiation pressure, and the pressure can make the beads trapped in the limited space, and which is called the optical trap. Okay, so the aim of today are the setting of the experiment, the Cas protein for on-target and off-target, and the mechanical force when Cas12 protein causes cleavage. The first result is that Cas12 protein binding and cleavage of lambda DNA. In figure 1 is a combination of optical tweezer with confocal influence microscopy and microfluidics, which the non-target strand is for green, target strand is for the gray, and the CRISPR RNA is for the red. In figure B, they use wild-type Cas12 protein and CRISPR RNA1 to binding, and lambda DNA was attached into two polystyrene beads here and be pulled by a force of 10 piconewton. This force allows scratching of the lambda DNA without altering its base pairing. Also avoid cleavage of the target DNA. And they perform binding experiment with the absence of magnesium ions. And when the white part inside here represent the binding of the assembled ribonucleoprotocol to lambda DNA. And figure C shows the presence of the magnesium ions causes sudden loss of the tension on the bed, which indicate the disruption of the DNA molecule. So this is the setting of the experiment. Okay, next, they increase the tension in 10 piconewton to 50 piconewton in 120 seconds to observe the binding of the Cas12 protein and the lambda DNA. For the second result, we can see that in higher tension, the more off-target binding, the white is a binding. And this behavior results in the DNA is falling apart. Its palm sequence is relatively inaccurate, which leads to the binding is mainly determined by CRISPR-RNA, and also leads to an increase in non-specific binding. The location of the target sequence is about 129 to 345. And we can see off-target is B1. And it happens only when the tension is big. In figure C of the binding is a ribonucleoprotein in multiple sites. Comparing with the 10 piconewton lambda DNA, binding is stable over 10 seconds. In 30 to 50 piconewton, as the tension is bigger, the off-target increases. This figure D shows this phenomenon. In normal cases, Cas binding towards the AT regions, which is because of the PAM sequence. But in high force, the RNP seems to accumulate the PAM mechanism and pairing by the CRISPR-RNA. Okay, in figure E, we can show the reproducibility between the increased tension and the binding. In low forces, binding determined by PAM. Instead, in high forces, binding determined by the sequence of CRISPR-RNA. And next, in the third result, they prove the off-target site by analyzing the lambda DNA sequence. All of these straight lines in figure A are the sequence same with the palm sequence in target and non-target strength, which the target strength is 29.707. And those off-target sequences are at 2.829 and 47.056, and also here about 13.329. And this is a figure about the target and off-targeting binding. The red part is the target sequence. You can also see here both the PAM sequence here and the CRISPR-RNA are well paired, while the green and blue part are the off-targeting part. And we can see only the PAM sequence pairing and only the front 4 NTR well pairing. Next, let's evaluate whether off-target binding leads to cutting. First, perform a cleavage assay using a target DNA of about 2,000 base pair long. And we can observe that there's a cutting in on-target but no cutting on off-target. On-target is this part. And cleavage in 2, but the off-target part has no cleavage. And in figure D, the lambda DNA shows the same result as in the 2000 base pair DNA. So for the second summary, you can see at low force, the on-target is well, and it's at 29.72. But in high force, the off-target increase, and it is at about 13.329. And when it is off-target or there is no magnesium iron, it doesn't cause the cleavage. Next, the fourth part. They analyze the cleavage of the Cas12 protein on lambda DNA. The tension applied to the lambda DNA was progressively increased from 0 to 60 piconewton and relaxed back in 50 seconds for 4 cycles. And figure 4a is for 1 cycle. And if there is a sudden drop in force happens before the cycles, they consider a cut by a Cas12a. And figure C is a condition without magnesium ions, and there is no dropping force observed. In figure 4b, it is a condition with the magnesium ion, and they observe the dropping force before a cycle, which means a DSB event. And this cleavage is at low force. So for the third summary, they observe the Cas protein cause the DSB events at low force, lower than 5 piconewton. And in before research, Cas9 protein is at about 40 piconewtons, great bigger than Cas12 protein. And that's today. Thank you for everybody's attention. And if anyone is more curious about the variant of Cas12 protein, you can go back to see the paper. Thank you.